Welcome to this walkthrough of LeetCode problem number 1389, create target array in the given order. In this session, we'll explore the problem, break it down step by step, and analyze the approaches to solve it effectively. Let's get started. In this problem, we are tasked with creating a target array using two input arrays, nums and index. Both arrays are of the same length. The goal is to build the target array by inserting each element from the nums array into the position specified by the corresponding value in the index array. To begin, the target array starts out empty. Then, as we iterate through nums, we take each element and insert it at the position indicated by the corresponding value in index. The problem guarantees that all insertion operations will be valid, meaning no out-of-bounds errors will occur. For the input format, the nums array can have a length between 1 and 100, and its elements can range from 0 to 100. The index array must be the same length as nums, and each value in index is constrained to be between 0 and the current position in the iteration, ensuring valid insertions at all times. The output of this problem is the final target array after all the insertions have been performed. Let's consider an example to understand this better. For nums equal to 0, 1, 2, 3, 4, and index equal to 0, 1, 2, 2, 1, the procedure is as follows. First, insert 0 at index 0, which gives us 0. Next, insert 1 at index 1, resulting in 0, 1. Then, insert 2 at index 2, making the array 0, 1, 2. After that, insert 3 at index 2, shifting the existing elements to get 0, 1, 3, 2. Finally, insert 4 at index 1, which shifts the elements again to produce the final target array of 0, 4, 1, 3, 2. This step-by-step approach highlights how each insertion modifies the target array. Now, let's look at another example. For nums equal to 1, 2, 3, 4, 0, and index equal to 0, 1, 2, 3, 0, the process begins by inserting 1 at index 0, resulting in 1. Next, 2 is inserted at index 1, making the array 1, 2. Then, 3 is inserted at index 2, giving us 1, 2, 3. After that, 4 is inserted at index 3, resulting in 1, 2, 3, 4. Finally, 0 is inserted at index 0, which shifts all the elements to produce 0, 1, 2, 3, 4. Let's examine a third example, with nums equal to 4, 2, 0, 3, 1, and index equal to 0, 1, 2, 2, 1. We start by inserting 4 at index 0, resulting in 4. Then, 2 is inserted at index 1, making the array 4, 2. Next, 0 is inserted at index 2, giving us 4, 2, 0. After that, 3 is inserted at index 2, shifting elements to produce 4, 2, 3, 0. Finally, 1 is inserted at index 1, yielding the final target array of 4, 1, 2, 3, 0. These examples illustrate how the algorithm handles different insertion scenarios. There are some important constraints and edge cases to keep in mind. First, the length of nums must be between 1 and 100, and it must match the length of index. Each value in nums must be between 0 and 100, while each value in index must be between 0 and its current position in the iteration. For edge cases, consider the minimum input case where both nums and index contain a single element, such as nums equal to 5 and index equal to 0. The resulting target array would simply be 5. On the other hand, for the maximum input size of 100 elements in each array, the solution must handle the operations efficiently. Additionally, cases with duplicate indices, as seen in examples 1 and 3, require the algorithm to correctly shift elements when inserting multiple values at the same position. Finally, the algorithm should also work correctly when nums or index is sorted in ascending or descending order. These constraints and edge cases ensure the robustness of the solution. To tackle this problem, the most straightforward approach is to directly follow the instructions provided. We iterate through the nums and index arrays simultaneously, and for each pair of values, we use Python's list.insert method to place the current number at the specified position in the target array. The algorithm begins by initializing an empty target list. Then, for every pair, number, IDX, from the nums and index arrays, we insert number at position IDX in the target array. Once all elements have been inserted, we simply return the target array.
While this approach is intuitive and easy to implement, the main drawback lies in its efficiency.
The insert operation in Python lists has a worst-case time complexity of O, n, where n is the current size of the list. Since we perform this operation for each element in nums, the overall time complexity becomes O, n squared. The space complexity, however, is relatively simple, as we only use the target array, leading to an O, n, space requirement, where n is the length of nums. The simplicity of the brute force approach comes with trade-offs. While it is easy to implement and directly align with the problem's instructions, the O, n squared, time complexity makes it inefficient for larger input sizes.
An alternative theoretical approach involves using a linked list instead of Python's built-in list. With a linked list, inserting at a specific position can be performed in O(1) time, assuming we already have a pointer to the insertion point. However, locating the insertion point still requires O(n) time in the worst case, which ultimately results in an overall time complexity of O(n squared, just like the brute force approach. Additionally, the space complexity remains O(n). While this linked list approach might appear advantageous at first glance, it has its own drawbacks. Python does not provide a built-in linked list structure, meaning implementing one from scratch would introduce additional complexity.
This makes the approach impractical for this particular problem. After considering the options, we chose to proceed with the brute force approach as the most practical solution. Although its time complexity is O(n squared, the problem constraints, specifically the maximum input size of 100, ensure that this solution runs efficiently within the limits. Its simplicity and alignment with the problem's requirements make it an ideal choice. A key insight here is that Python's list.insert method already performs the exact operation needed for this problem. Leveraging this built-in functionality simplifies the implementation significantly.
While alternative strategies, such as using a linked list, could theoretically reduce insertion costs, the lack of a built-in linked list in Python and the additional complexity of implementing one outweigh any potential benefits.
This realization highlights the importance of balancing theoretical efficiency with practical implementation, especially when problem constraints favor simpler solutions. In terms of complexity analysis, the brute force approach has a time complexity of O(n squared, as the insert operation is performed for each element in the nums array, with each operation taking linear time in the worst case. The space complexity is O(n), which accounts for the storage of the target array. This approach represents a balance between simplicity and efficiency, making it the most suitable choice for this problem given the constraints. While alternatives like linked lists might offer theoretical benefits, the practicality and clarity of this method, combined with its ability to handle the input size efficiently, solidify it as the preferred solution. In this problem, we're given two arrays, nums and index. The nums array contains the elements we need to insert into an initially empty target array, and the index array specifies the positions where these elements should be inserted. Our task is to construct the target array following these rules and return it. For example, if nums is 0, 1, 2, 3, 4, and index is 0, 1, 2, 2, 1, we build the target array step by step by inserting each number from nums into the position specified by index. The final result is 0, 4, 1, 3, 2. To achieve this, we'll explore a straightforward brute force approach that adheres to the instructions step by step. The algorithm begins by initializing an empty list, target, which will eventually hold the constructed array. We then iterate through the nums and index arrays simultaneously, processing each pair of elements. For each pair, number, IDX, number is the value from nums that we want to insert, and IDX is the position in the target array where this value should be placed. To perform the insertion, we use Python's list.insert, index, element, method, which inserts number at position IDX in the target array. This operation automatically shifts all existing elements at or after IDX one position to the right, ensuring that the order is maintained. We repeat this process for every pair until all elements are inserted into the target array. Once all the elements from nums have been inserted at their respective positions in target, we simply return the fully constructed array as the result. A few key insights make this algorithm particularly effective. First, it leverages the behavior of Python's list.insert method, which handles shifting elements to preserve the correct order. This ensures that even with multiple insertions at the same position, the array remains consistent. Additionally, the algorithm handles edge cases like empty input arrays, duplicate indices, or boundary indices seamlessly.
For example, if nums and index are both empty, the result is an empty list. If an index is repeated, the subsequent insertions are handled correctly by shifting elements. And if IDX is 0 or equal to the length of target, the element is inserted at the beginning or appended to the end, respectively. For this problem, we use a list as the primary data structure to construct and store the target array. Lists in Python are dynamic, meaning they allow for efficient appending and insertion operations. The choice of a list is ideal because the insert operation directly implements the behavior required by the problem. When we need to insert an element at a specific position, the list automatically shifts the subsequent elements, ensuring that the insertion rules are followed without additional manual adjustments. Furthermore, the dynamic resizing capability of lists enables us to handle arrays of varying sizes without needing to pre-allocate memory, making this data structure both practical and efficient for our needs. Analyzing the complexity of this algorithm, we observe that the list.insert operation has a time complexity of O(n) in the worst case. This is because inserting an element at an arbitrary position may require shifting all subsequent elements to the right. For an input size of n, we perform n insertions, where the cost of each insertion increases sequentially from O(1) up to O(n). When summed, the total time complexity becomes O(n squared). In terms of space complexity, the algorithm uses O(n) additional space to store the target array, which grows as we insert elements. Other than this, no extra memory is allocated, so the overall space complexity remains O(n). Let's walk through an example step by step to see the algorithm in action. The input arrays are nums equals 0, 1, 2, 3, 4, and index equals 0, 1, 2, 2, 1. We start with an empty target array. First, we insert 0 at index 0, resulting in 0. Then, we insert 1 at index 1, making the array 0, 1. Next, we insert 2 at index 2, giving 0, 1, 2. After that, we insert 3 at index 2, which shifts the existing elements and updates target to 0, 1, 3, 2. Finally, we insert 4 at index 1, resulting in the final array 0, 4, 1, 3, 2. This matches the expected output, demonstrating that the algorithm correctly constructs the target array following the specified rules. This solution implements the createTargetArray in the given order problem. The createTargetArray function takes two input lists, nums and index. First, we initialize an empty target array to construct the result. Then, we iterate over each element of the nums and index lists using a for loop. For each iteration, we use the insert method to insert nums, I, at the position specified by index, I, in the target array. Python's list.insert handles shifting elements automatically to make room for the new element. This ensures that the target array is constructed in the correct order. Finally, we return the target array as the result. The solution is efficient for the problem size, and edge cases, such as empty inputs, are naturally handled due to the mechanics of the insert method. Here, we start by importing the necessary packages and defining our solution class. Inside the createTargetArray method, we take two input arrays, nums, which contains the values to be inserted, and index, which specifies the positions where these values should be inserted. We first initialize an empty array list called targetList to dynamically build our target array. Then, we loop through both the nums and index arrays simultaneously using a for loop. For each iteration, we use the add method of the ArrayList to insert the current element from nums at the specified position from the index array. This dynamic insertion allows us to rearrange the elements in the desired order efficiently. Once the loop is complete, we convert the target list into a regular integer array. This is done by iterating through the target list and copying each element into a new array called targetArray. Finally, we return the resulting target array as the output of the method. This approach ensures that we maintain the correct order while adhering to the constraints of the problem. In the main method, we demonstrate how to use the createTargetArray method. We define two example arrays, nums and index. The nums array contains the values 0, 1, 2, 3, 4, and the index array specifies the positions 0, 1, 2, 2, 1. By passing these arrays into our method, we get the resulting target array. When printed, the output is 0, 4, 1, 3, 2, which matches the problem's requirements. This output is achieved by inserting each number from nums into the target list at the corresponding position from index, while dynamically shifting elements to accommodate each insertion. This example helps illustrate how the solution works in practice and confirms that the implementation produces the correct result. In this problem, we need to construct a target array by inserting elements from the nums array at specific positions defined by the index array. The challenge lies in handling cases where positions in the target array are already occupied, as we need to shift elements to the right to make space for new insertions. To understand this better, let's walk through the solution step by step using the first example. Here, nums is 0, 1, 2, 3, 4, and index is 0, 1, 2, 2, 1. Initially, the target array is empty. First, we insert nums 0, which is 0, at position index 0, which is 0. Since the target array is empty, this is straightforward, and the target becomes 0. Next, we insert nums 1, which is 1, at position index 1, which is 1. At this point, the target array becomes 0, 1. Then, we take nums 2, which is 2, and insert it at position index 2, which is 2. Again, there's no need for any shifting, so the target becomes 0, 1, 2. Now, we move to nums 3, which is 3, and insert it at position index 3, which is 2. Since position 2 is already occupied, we shift the existing elements at and after this position to the right before inserting 3. This updates the target to 0, 1, 3, 2. Finally, we insert nums 4, which is 4, at position index 4, which is 1. Again, we shift elements starting at position 1 to the right, resulting in the final target array of 0, 4, 1, 3, 2. Now, let's look at the second example with nums as 1, 2, 3, 4, and index as 3, 1, 2, 0. Initially, the target array is empty. The first step is to insert nums 0, which is 1, at position index 0, which is 3. Since the target is empty, it simply becomes 1. Next, we insert nums 1, which is 2, at position index 1, which is 1. This updates the target to 1, 2. Then, we take nums 2, which is 3, and insert it at position index 2, which is 2. Again, no shifting is required, so the target becomes 1, 2, 3. Finally, we insert nums 3, which is 4, at position index 3, which is 0. Since position 0 is already occupied, we shift all existing elements to the right and insert 4 at the start. The resulting target array is 4, 1, 2, 3. The final output for this example is 4, 1, 2, 3. Let's now consider a third example where nums is 5, 6, 7, and index is 0, 0, 0. Initially, the target array is empty. First, we insert nums 0, which is 5, at position index 0, which is 0. This makes the target array 5. Next, we insert nums 1, which is 6, at position index 1, which is also 0. Since position 0 is already occupied, we shift the existing element to the right and insert 6 at the start. The target becomes 6, 5. Finally, we insert nums 2, which is 7, at position index 2, which is again 0. As before, we shift all existing elements to the right and insert 7 at the beginning of the array. This results in the target array 7, 6, 5. The final output for this example is 7, 6, 5. To summarize, the process involves iterating through the nums and index arrays and using the insert method to place each element in the correct position. The insert operation dynamically shifts elements to ensure the target array is updated correctly. While this approach is effective, it has a time complexity of n squared, due to the cost of shifting elements during each insertion. The time complexity of this solution is driven by the insert operation within the for loop. To break this down, the insert operation in Python has a time complexity of k, where k is the number of elements that come after the insertion point. This is because inserting at a specific index requires shifting all subsequent elements one position to the right. Now, if the insertion happens at the end of the list, no elements need to be shifted, so the operation is O1. However, if the insertion occurs at the start of the list, all elements have to be shifted, making it len target in the worst case. On average, the insertion index is somewhere in the middle of the list, resulting in approximately half the elements being shifted. This gives an average time of n for one insert operation, where n is the current length of the target list. Since the loop iterates m times, where m is the length of nums, the cost accumulates over all iterations. On the first iteration, the insertion cost is 1, on the second it is 2, and so on until m1. Summing these costs leads to a total time complexity of 1 plus 2 plus 3 plus m1, which simplifies to m squared. This summation, representing the accumulation of insertion costs across all iterations, simplifies to m squared, based on the formula for the sum of the first m1 integers. So, the final time complexity of the solution is m squared, where m is the length of the nums list. Now, looking at the space complexity, the main factor is the space used by the target list. Since this list is built incrementally and grows to match the size of nums, it will contain up to m elements, resulting in a space complexity of m. Beyond this, no additional data structures are used in the solution, so the space footprint is minimal compared to the time cost. If we compare this approach to a more naive implementation where indices and elements are manually shifted, the time complexity remains m squared. The key difference is that the use of Python's built-in insert method achieves the same result more efficiently in terms of implementation, though it doesn't reduce the time complexity. Even with optimizations, such as using a linked list instead of a Python list, the overall time complexity wouldn't change. While insertions in a linked list would be 1, traversing to the correct insertion point would still require n, maintaining the same m squared complexity. In summary, the time complexity of this solution is m squared, where m is the length of the nums list. The space complexity is m, as the space required is proportional to the size of the target list. While the solution is simple and effective given the constraints of the problem, it becomes less efficient for very large input sizes due to the quadratic time complexity. However, given the nature of the problem and the constraints provided, this trade-off between simplicity and performance is reasonable and ensures clarity in implementation. When tackling this problem, there are a few common mistakes that developers often encounter. First, a frequent error is using the append method instead of insert. While appending adds elements to the end of the list, the insert method is crucial here because it places elements at the specified indices. Without using insert, the placement of elements in the target array will be incorrect, especially when the index order is crucial. Next, it's important to handle duplicate indices properly. If the index array contains duplicates, the insertion order of nums must be strictly followed to ensure deterministic behavior. Neglecting this can lead to unexpected outputs. Additionally, modifying the target array while iterating over it can cause logical errors. For example, inserting elements while simultaneously reading from the same list can disrupt the intended sequence. To avoid this, you should use separate loops or carefully structure the operations to prevent in-place modification during iteration. Another pitfall is ignoring edge cases. Failing to account for scenarios like an empty nums array, an empty index array, or mismatched lengths between the two can result in runtime errors. To address this, always validate your inputs and test for these specific edge cases during implementation. Some developers also overcomplicate the solution by introducing nested loops unnecessarily. This leads to inefficient n squared time complexity, which is avoidable. Instead, focus on a straightforward single-pass approach through the nums and index arrays. From an interview perspective, this problem is designed to test your array manipulation skills and your understanding of operations like insert. It's important to show that you can work with dynamic lists effectively. While Python's insert method is a convenient choice, be prepared to discuss its trade-offs, such as the n complexity per insertion. During interviews, clearly explain your thought process, highlight how you handle edge cases, and justify your choice of data structures. If time allows, you can also discuss potential optimizations, like switching to a linked list for faster insertions. This problem is also closely related to others on LeetCode that test similar concepts. For example, count of smaller numbers after self involves more advanced techniques like segment trees or binary index trees, while insert interval focuses on insertion logic in a different context. Additionally, design hash set examines insertion principles but applies them to hash-based data structures. When considering alternative approaches to solve this problem, one option is the brute force method. This involves iterating through the nums and index arrays and using the insert method directly for each element. However, this approach can result in a time complexity of n squared, in the worst case, due to the repeated shifting of elements during each insertion. Another option is to use a linked list, which allows for faster insertions at arbitrary positions. While this reduces the cost of insertion to 1, it comes with its own trade-offs, such as increased memory usage and slower traversal times. Lastly, there's the simulation approach, which involves constructing the target array by simulating the insertion process using auxiliary data structures. For example, you could use a deque or even implement a custom data structure tailored to this problem. This approach can be beneficial in languages where direct list insertion is less efficient or where you need greater control over the underlying operations. Each of these approaches has its strengths and trade-offs, so it's important to evaluate them based on the constraints and requirements of the problem. Whether you choose the straightforward method or explore alternatives, the key is to ensure your solution is both correct and efficient. Great job! We've summarized the key points of the solution, including the algorithm, time complexity, and space complexity. Remember to practice similar problems to reinforce these concepts. Thank you for joining me, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!